Pankaj, Urvashi, both are there.
Yeah.
So, yeah.
Okay.
So, okay. So, Alok, you can formally start, yeah?
Okay, sure. So, welcome to this post-lunch session. And I thank Professor Manigrahi for giving me the opportunity to introduce the speaker of this session, Professor Jonathan Halliwell. And it is indeed our great pleasure to have Jonathan with us today. Professor Halliwell is currently a professor at Imperial College London, and he received his PhD from Cambridge University in 1986. And his early career was focused on the quantum gravity and quantum cosmology. And you'll be pleasantly surprised to know his PhD supervisor, Stephen Hawking. And after his PhD, he held a couple of postdoc positions at the University of California, Santa Barbara and MIT. He then came back to join Imperial College in 1992, initially as a Royal Society University Research Fellow, and then became lecturer, and finally became the professor in 2002. He works in the diverse area, and along with the quantum gravity and quantum cosmology, he has a strong interest in the quantum foundations, interpretation of quantum theory, in particular the decoherent histories approach to quantum theory. He has also worked in the timing quantum theory and a deep conceptual issue that is yet to be settled. The last 5 years, he has been working very actively on another important and deep foundational issues, the notion of macrorealism, and the question of the compatibility and incompatibility with the quantum theory. And he wrote quite a number of interesting papers in that topic. And in fact, I learned a lot from these papers. And I'm also grateful to him for the several email correspondence with him regarding this topic. So today we got the opportunity to listen to him, and he will be talking about the various aspects of Leggett-Garg test of macrorealism. And with this word, I would like to invite Jonathan to deliver his lecture.
Good. Okay. Well, thank you very much, Alok, for that generous introduction. Actually, first of all, can you hear me okay? Just give me a thumbs up.
Yeah, it's perfect, I think. Yeah.
All right. The second problem is screen sharing. Let's have a go at that. We had a little practice yesterday. Okay, this should be the first slide of my screen. Can you see this okay?
Sure, it's perfect, yeah.
Okay, good. Well, it's a great pleasure to have a chance to speak with you today. As you see from the title, I'm going to be talking about a number of aspects of the Leggett-Garg approach to macrorealism. First of all, I'd like to just start in these difficult times by giving thanks to various people. First of all, the organisers of the summer school, and then a whole variety of people I've had a good chance to talk to and work with over the last few years. So recently, I've had some very enjoyable interactions, actually the last few years, with Alok Pan and Dipankar Home, and then more recently with some brief interactions with Abasi Sinha in connection with the wonderful experiment that her lab has done, which I'll be mentioning briefly. Then a lot of my work has been done with my PhD students, most recently Clement Morby, some time ago James Yearsley, and also a couple of recent papers with my collaborators Cheyenne Majidi and Ramon Laflamme at the IQC in Waterloo in Canada. I've also had a chance to do some projects with undergrads and master's students. Leggett-Garg Inequalities is actually a very nice area for them to do work on. And then here in England and Europe, there are a bunch of other Leggett-Garg enthusiasts that I try to talk to when I can. So thanks to all of them. This also just gives you socially a sense of who I'm connected to and who I'm talking to. So the general story around Leggett-Garg, it concerns the question that Einstein posed a long time ago: is the moon really there when no one looks? Or more specifically, can a quantum system be thought of as following a definite trajectory, irrespective of whether or not it's being measured? An alternative way of saying this is, can macroscopic systems exist in superposition states? A question of perennial interest and continues to be a very interesting one as experiments advance towards the state where we may actually be able to check this idea. From a broader perspective, this relates to questions of classicality in quantum theory. I used to work actually in decoherent history's approach to quantum theory and emerging classicality. Their classicality is defined, well, there's a hierarchy of classicality conditions, but decoherence is perhaps one of the most commonly studied ones, but decoherence is a kind of asymptotic condition under very coarse grain scales. But the interesting question is, as you go to much finer grain scales, to what extent can you still talk about quantum systems in a classical way? Macroscopic realism is perhaps the weakest notion of classicality. It basically says, can a given experimentally determined data set have a classical simulation? Well, the Leggett-Garg Inequalities were designed to test this very specific and rather weak notion of classicality. There are other notions that appear in this field, like no signaling in time, which are somewhat stronger. They live a little bit higher up the hierarchy, and some of these I will mention briefly. So that's the broad sort of picture of what Leggett-Garg Inequalities are about. Now, what am I going to do in this talk? Well, I will start in the first few sections by a review of Leggett-Garg Inequalities. I'll start actually with Bell experiments and then move over into the Leggett-Garg framework, the temporal analog of that. And then I'd like to devote a chunk of time to actually developing and extending the standard Leggett-Garg framework. The original framework provided necessary conditions for macrorealism, not necessary and sufficient ones, but they can be extended in that way, and this is what I'll describe, and it gives more decisive tests and also a clearer parallel with Bell experiments. Then, over the last few years, I've done a certain amount of work on generalizing all of these things further to various ways, more times, higher order correlators, many variables, so I'll briefly mention that. And then two particular questions that are very relevant in the Leggett-Garg story is, first of all, how to do measurements that are non-invasive, as I'll describe. In order to do successful Leggett-Garg experiments, you have to find ways of measuring things non-invasively. There's a lot of debate around that, so I have some thoughts on possible improvements to that story. And then the other big question in the Leggett-Garg story is about approaching macroscopicity. And there have been some interesting recent ideas showing how interferometric tests or simple harmonic oscillator systems can be made use of to approach macroscopicity. So the part of this that is my work is described on a bunch of recent papers with students and collaborators. The detailed references are actually listed on my abstract. Okay, well, let's just start with the more familiar case of an EPRB experiment, just to set the ground, because everything we're going to do is going to be a parallel of this situation. So we make measurements on a pair of particles in an entangled state that are a long way apart, and that allows us to determine a data set which consists of a bunch of joint probabilities on one particle and the other particle. So for instance, the 1,3, the 1,4, the 2,3, the 2,4 probabilities, where this label S is plus or minus 1. And these will indicate correlations between these particles, and we can start to try and understand these things in a classical sense. These pairwise probabilities will obey a no signaling condition, which mathematically it means that these pairwise probabilities are compatible with each other on their overlaps. So if any two of them involve the 3 measurement, then the two corresponding pairwise ones must be compatible in this way. And in order to try and find an underlying classical model, we suppose there's an underlying joint probability of which these 4 probabilities are marginal probabilities. And if such a probability exists, then if we compute these familiar correlation functions, they must satisfy the 8 inequalities of the Clauser-Horn-Shimoni-Holt type. So 2 of which are here, and then there are 6 more of these. So these are necessary conditions for local realism. Now, one can't make a stronger statement than that. There is the famous theorem, due to Arthur Fine, which says that the 8 CHSH inequalities plus the no signaling conditions are also sufficient conditions for the construction of this underlying joint probability distribution. So CHSH plus no signaling are necessary and sufficient conditions for local realism. So this is a very powerful result in Bell experiments. Similar statements also occur with Bell inequalities in which you do 3 measurements. And I mention these because we will work with the analog in the Leggett-Garg case of these 3 correlator measurements. Now, it's this basic structure which we're going to try and take over into the Leggett-Garg framework. The existence of this underlying probability here is, note, deduced indirectly from the partial snapshots. You don't, in Bell experiments, you don't actually measure this thing. It is about trying to see whether or not a bunch of partial snapshots have a joint underlying reality. In quantum mechanics, however, you can in fact try and attempt to measure joint probabilities like this. Well, yes, you can attempt to measure them. In some approaches to quantum mechanics, like decoherent histories, you can attempt to find candidate probabilities for these things. And there's quite a long story there I won't go into, but the short conclusion is that inequalities like the Bell or CHSH inequalities imply bounds on the degree of interference in quantum mechanics. So from a quantum mechanical perspective, you don't need zero interference to satisfy these inequalities. You just need the interference to be suitably bounded in some way. And that will be significant in what I say next about Leggett-Garg inequalities. Okay, well, just moving on to the Leggett-Garg tests. So these were first proposed in 1985 as
Jonathan, we lost the full screen mode.
Okay, I just did a slight adjustment here. Let me go back again. Thank you for telling me that. Actually, certain things happen with the full screen mode which stop me from seeing all of it, but I shall persist with this. Okay, so yeah, Leggett-Garg inequalities were proposed in 1985 to test as a temporal parallel. They test this notion of macrorealism that I've given a loose version of, but they break the definition of this down into 3 different separate assumptions. So the first system is often called macrorealism per se, the idea that the system is in a definite state at each moment of time. By the way, this field is rather replete with jargon and acronyms, and I'm trying to keep these under control, but just be warned, we use a lot of these acronyms throughout the subject area. The second assumption is non-invasive measurability, the idea that the state can be measured without disturbing subsequent dynamics. And a third assumption, which is rarely a challenge, is that future measurements don't affect the present state. This is often called induction, not a particularly good nomenclature. It might be better just to say there's no retrocausality. In any event, this is rarely challenged. So the interesting ones are the first 2, macrorealism per se and non-invasive measurability. So macrorealism is then the logical conjunction of these 3 separate assumptions, and this is what we are trying to test in Leggett-Garg tests. Now, for those of you not familiar with the subject, I can recommend the review by Emery et al. In 2014. Also, there was a very penetrating critique of the whole area by Moroney and Timpson around the same time, which I also heartily recommend for anyone interested. So here's how it works out in a specific situation. So we imagine that we make measurements on a single dichotomic variable Q, which could be a spin, at pairs of times. So there are 4 possible measurement times, but in each experiment you only measure 2. So the 1, 2, 2, 3, 3, 4, and 1, 4. And from those you determine a set of correlators, temporal correlators, which, by the way, note exist in a cycle, 1, 2, 2, 3, 3, 4, 1, 4. You don't measure all of them. I will come back to that bit somewhat later on. And then under the assumptions of macroscopic realism, a joint probability must exist for the values of Q at these times. And that then implies that these correlators must obey the so-called 4-time Leggett-Garg inequalities, which are identical in form to the CHSH inequalities up to some relabeling of these numbers. So there are 2 of them here plus an extra 6. So there are 8 4-time Leggett-Garg inequalities. And these are necessary conditions for macrorealism. If violated, macrorealism is violated. Now, the first observation is that quantum mechanics can violate these inequalities very readily. One commonly looks at simple spin systems. So we take Q to be just A dot sigma in some, for a Pauli matrix in some direction A. If I take the Hamiltonian to be sigma x, the correlator in a quantum treatment has this form, just the anti-symmetrized Qs, and it's just a cosine. So completely analogous to EPRB, and not surprisingly, as you know in EPRB experiments, the cosine form can very easily violate these inequalities. And indeed, typically what we do is take equal time spacing, you get correlators of this form, and there's a maximal violation of 2 root 2, that's omega t is pi by 4. This is the so-called Tilson bound, so you can easily reach that bound. So that's for simple spin systems, and there have been many theoretical and experimental tests with simple systems of this type. One of the big goals, as I've said already, one of the big goals of this approach, of the Leggett-Garg approach, is to move away from simple systems like that to genuinely macroscopic ones, and I'll be saying some words about that towards the end. Now, the other big issue is about maintaining non-invasiveness of the measurements. These measurements, when you do sequential measurements, just going back a bit, you see in this situation, I have to measure at T1 and then at T2, and you can always say, well, actually the measurement at T1 was disturbing, and that's what produced the correlator. It isn't necessarily due to the underlying properties of the system. So we try to do non-invasive measurements to eliminate alternative explanations. There have been specific models, for instance, Montino and Yearsley dreamed up specific invasive models which showed that you can quite easily choose the invasiveness so you get exactly the quantum correlators. So it's not hard to actually explain the quantum results if invasiveness is allowed. The way this is normally handled is was proposed by Leggett and Garg in the first paper to use ideal negative measurements in which you couple the detector to one side only, for instance, the QS plus 1 state. And then you say a null result implies that Q must be equal to -1. This was implemented in some of the first important experiments of Leggett-Garg, like the first one by NIM in 2012, and most recently by the experiment in the Sinha lab, which imposes this in a particularly compelling way with additional checks. There is a complication here, though. From the quantum mechanical point of view, ideal negative measurements still cause wave function collapse, which rather confuses the interpretation of any checks on invasiveness. Are you measuring genuine invasiveness or wave function collapse? This we can come back to. One of the earlier experiments on Leggett-Garg actually used weak measurements, but the issue here is that weak measurements, you're measuring a very small effect, and often the disturbance is the same magnitude. So to what extent does a weak measurement really implement non-invasiveness? I think there's still a debate there as to what degree that's actually really true. One final comment here, that the measurements often involve an ancilla, an auxiliary system that becomes entangled with Q at the first time. Now, what that means, in fact, is that in a Leggett-Garg test, you actually end up with 2 systems in an entangled state. So from that point of view, it is quite similar to EPRB. So that's one reason why there's a lot of close parallels between Leggett-Garg and EPRB experiments. Now, just as an aside here, this is one way, this is a probably unreachable goal, but this is one way in which you could get a very convincing non-invasive Leggett-Garg test using an EPRB pair. you basically take your Leggett-Garg system to be half of the EPRB pair, the half on the right-hand side over here. And what I do is prepare this entangled state. The two particles shoot off great distance away. The first time you measure the particle on the left, and you use the correlation to deduce the value, the anti-correlation, to deduce the value of the particle on the right at that time, but without actually measuring it directly. And then you wait a little while, and then you measure the particle on the right at time t2. So you've actually done a non-invasive, using the locality, you've done a non-invasive measurement to determine Q at both times. Now, this is harder than a Bell test because you have to take in you have to allow this extra time on the right-hand side over here. But this is the sort of thing that might be required in Leggett-Garg tests in order to get a convincing story around non-invasiveness. Now, some comments now on Leggett-Garg framework generally. What is it trying to do? Well, it's trying to refute macrorealism, or more specifically, to actually rule out certain types of hidden variable theories, or ontic models, as they're more commonly called these days. The theory was originally devised to rule out hidden variable theories of a particular type, namely quantum mechanics plus a superselection rule. So theories in which you suppose that there's some sort of superselection rule operating at large scales that kills coherent states. These are closely related to GRW theories, of course. There are other hidden variable theories that don't fare so well in Leggett-Garg tests, for instance, de Broglie-Bohm, unless you can invoke some sort of locality. Moroni and Timpson, and also before that, Baccia-Galuppi, made that point quite strongly in the early days. So really, Leggett-Garg tests are only convincing in ruling out these sorts of theories, quantum mechanics plus superselection. One now key issue that is the difference between EPRB experiments and Leggett-Garg ones concerns these no signaling relations that we expect to hold in Bell tests, but not in Leggett-Garg, because you're doing sequential measurements. So these don't hold, and because of that, Fine's theorem doesn't hold, because you need these to hold in order to have the probabilities being compatible with each other on the overlaps. Now, that means that the Leggett-Garg inequalities are necessary conditions for macrorealism, but they're not sufficient. So they are weaker than the Bell tests. So now let's take some time to actually address exactly this point and to show how you can actually make better tests, which are necessary and sufficient to get around the difficulty that these things aren't satisfied. So let's just moving here then into part 3 of the talk. So for temporal correlations in Leggett-Garg tests, the analog of no signaling is called the no signaling in time condition, first put forward by Bruckner and Koffler in 2013. Now, here you imagine doing measurements at 2 times and then summing out the first measurement, and then comparing it with the measurement at the second time only with no earlier measurement. And the no signaling in time condition is the condition that this doesn't make any difference. Now, this actually combines 2 different things. It, in effect, combines both non-invasive measurability and MRPS. So that's another sort of source of confusion, just separating an understanding of these 2 things. However, when it holds for all pairs of measurements, Fine's theorem applies, and then there's no problem. So then you do have necessary and sufficient conditions. But as I said on the previous slide, this doesn't hold in general in quantum mechanics for sequential measurements. So what do we do about this? Well, what Bruckner and Koffler did was to say, well, let's look at alternative definitions of macrorealism that use no signaling in time conditions only without using the Leggett-Garg inequalities. Now, so they did a whole bunch of conditions of this type. It's a completely valid way to proceed, but they're extremely stringent conditions that are only satisfied for 0 quantum interference. So in other words, they're actually rarely satisfied. It also departs from the spirit of Bell inequalities, and it's not a parallel of Bell. There is, however, a different way of meeting Fine's theorem using a different implementation of non-invasiveness, doing setting up the experiment in a different ways, doing different sorts of measurements, in which you kind of formally satisfy this condition but without the conditions being too stringent. So here's how it works. The story you see is that if you're measuring Qs that don't commute at different times, the existence of a joint probability is just not guaranteed. I mean, that's the standard thing in quantum mechanics. When you're talking about pairs of non-commuting variables, you can't in general find a satisfactory probability for both of them. This means, therefore, that macrorealism will fail already at the two-time level, unlike EPRB experiments. And even if it is satisfied, there's probably a number of different ways of assigning probabilities to pairs of non-commuting observables. These different probability assignments just correspond quite simply to different measurement protocols and different implementations of NIM. So you can actually get around this if you just look at different ways of finding the two-time probability. So here's the suggestion. We have at two times, there are three things we can measure. You can measure the average of Q at time t1, average of Q at time t2, and the correlator. And what we do is to do this not in one run, but you do it in three separate experiments. So you only need, because in the first two there's only one measurement, you only need to worry about non-invasiveness when you measure the correlator. And then you say, well, let's actually just try to indirectly construct the joint probability from its moments. And there's a standard construction of that two-time joint probability from its moments. It's just this expression here. I've called it Q because it's right now it's a quasi-probability. It may or may not be positive. In a macro-realistic theory, where a relationship like this must hold because Q and S are both plus or minus 1, and if you average that, you find that Q actually must be positive. So Q is actually positive when macrorealism holds. In actual fact, it's quite easy to see that Q positive is a necessary and sufficient condition for macrorealism at two times, because Q is actually the probability for this data set. So Q is actually a measure of MRPS at two times. If it's negative, MRPS fails at two times. So this simple little observation is actually the key to making all of this work, just by doing three different experiments and indirectly assembling this joint probability. This gives us the desired probability two times, which makes Fine's theorems work. Now, this means, therefore, in terms of implementing non-invasiveness, there are actually two different ways of doing this. And this extends to higher order cases as well. So the first one is what I've just done here. And I call this piecewise non-invasive measurability. So it means that you collect the data set in a bunch of different pieces. You do numerous experiments to measure all the moments. And you only require non-invasiveness in each individual experiment. And then you indirectly deduce the probability, the two-time one in this case. So that's what I'm going to be doing for most of the rest of this, this part of the talk. The alternative is what Koffler and Bruckner suggested, which is you just measure everything in a single experiment, and then you impose the much more stringent no signaling in time condition. So this can be extended also to 3 and 4 times. I'm not actually going to do this here. I'm just going to concentrate on the so-called piecewise NIM, which incidentally is, I think, the essence of what is done in most Leggett-Garg experiments, although they don't necessarily say that explicitly. So here's how we do it at 3 times. You do either piecewise NIM, you do numerous non-invasive experiments in measurements in different experiments, and they're depicted here. So we do, for instance, 3 experiments to get the 3 correlators in 3 different experiments, or you can do it using sequential non-invasiveness, where you measure everything in one go, and you actually measure the joint probability for the 3 measurements. In the piecewise version, you deduce the 3-time probability indirectly. In fact, what you deduce is that there's a whole family of 3-time probabilities that match the data. Now, as I said, we're just going to concentrate on the piecewise version. So at 3 times, we measure this data set, 3 correlators, 3 single-time averages in 6 different experiments. Sometimes you can make a few shortcuts and get it down to a smaller number, but you do it in enough different experiments so that earlier measurements aren't affecting later ones. And then the general question is, can you match this to an underlying joint probability? And you can do this in 3 steps. Single-time probabilities are trivially found. The 2-time probabilities are found if the 2-time Leggett-Garg inequalities hold, and that would be true for a macrorealistic theory. Now, the thing with these 2-time joint probabilities is that they actually satisfy no signaling in time, in quotes, by construction, which means the conditions for Fine's theorem are met. So these 2-time ones are compatible on their overlaps, which is the mathematical requirement for Fine's theorem to hold. It doesn't say anything about signaling because we're not measuring them sequentially, so they formally satisfy no signaling condition, but this formal satisfaction is actually enough to make the whole construction work. So the 3rd step is then to realize that this now gives us, in fact, an exact mathematical parallel with the Bell case. And Fine's theorem then says that the joint probability exists if and only if the 4 Leggett-Garg inequalities hold at 3 times, plus the 12 2-time ones. So that's it. These are the necessary and sufficient conditions for macrorealism at 3 times for the data set in which you measure the 3 averages of Q and the 3 correlators. And these test a very specific version of macrorealism, which I call weak macrorealism, for reasons I'll come back to in a minute. And it comes down to the following. So its non-invasiveness is imposed in a piecewise way in each separate experiment, logically conjoined with a set of 3 2-time inequalities and the 3-time inequalities, and in the trivial one, induction. Now, this is, I think, what is probably the underlying concept in a lot of Leggett-Garg tests, if you like, as a completion of many of the original proposals, elevating things from necessary to necessary and sufficient. Now, I call it weak because you can strengthen these things to a NIM which involves no signaling in time, and then you replace all these things with no signaling in time conditions. But this is the weakest one possible, I think, the weakest interpretation of what we think Leggett-Garg tests are about. Now, you can very readily generalize that to 4 or more times. I'll say a little bit more about that later on. So a few comments here. So these 12 2-time Leggett-Garg inequalities provide the extra restrictions that elevate the 3-time inequalities up to necessary and sufficient conditions. How would we test these experimentally? Well, actually, it's pretty easy. Most of the experiments have already measured bunches of correlators. It's much easier to actually measure the 3-time averages. In fact, in some cases, it might already be there in the data just to figure out what these things are. In 2019, Shayan Majidi in Ramon Laflamme's lab in Waterloo carried out an explicit experiment in an NMR test, which measured all these data sets, and that was actually a full set of 12 of 2-time and 3-time Leggett-Garg inequalities, and hence a very decisive measurement of macrorealism. Some people have said to me, I've never seen a 2-time Leggett-Garg inequality before, what's this? Well, actually, they used a lot already in existing tests. So if I take a standard 3-time inequality like this, for instance, and then just take T1 to be the initialization time and take Q1 equals 1, this collapses down to a 2-time inequality. In fact, I asked Clive Emery, who wrote the review article, how many experiments do this, and actually about half the tests that have been done to date actually test 2-time inequalities, not 3-time ones. So the 2-time ones are actually out there. So in effect, what I've actually done with these new conditions is to gather together a lot of bits and pieces that are already there in the theoretical and experimental literature, and to show that you can make them into necessary and sufficient conditions, which are decisive tests. So a few more comments here. From a quantum mechanical point of view, 2-time and 3-time Leggett-Garg inequalities detect the presence of independent interference terms. So interference terms are 2 times, and at 3 times. Now, as a consequence, the LG2s and the LG3s can be satisfied or violated independently. So in a thorough search of parameter space, there are generally four regions. So both satisfied, both violated, one satisfied, the other violated, and so on. Some regions are more interesting than the others. If the 2-time ones are violated, then macrorealism is already lost, at least for that data set. So from that perspective, there's no need to check the LG3s. On the other hand, that means that LG3 violations are clearly most interesting when the 2-time Leggett-Garg inequalities are already satisfied. And that actually is the sort of what happens in Bell experiments. But in the parallel Bell experiments, the LG2s will be trivially satisfied. So LG violated with LG2 satisfied is a natural parallel with Bell. But now we can ask another question. Supposing you actually have a model and you check it experimentally, you can find all the LG2s are satisfied and all the LG3s are satisfied. So you would say, at least for that particular data set, macrorealism holds. But we think in the background, there is still quantum behavior. So if all of these things are satisfied, where is the quantum behavior? What do we actually need to do in order to find it? Well, this brings me on to the next part of the talk, which is to say, well, what we do is to go to extended data sets. We go to finer grained descriptions of the system to try to find the quantum behavior that we think is there. So we take data sets that consist of the averages and the correlators, but we go to more times, we measure higher order correlators, and we look at more variables. So there's a bunch of papers being written about this over recent years, and again, with Cheyenne Majidi and Ramon Laflamme, we gathered all these conditions together in a recent paper with a view to exploring parameter ranges in specific spin models in the hope of doing experimental tests in the foreseeable future on these extended data sets. Now, what these different conditions look like is as follows. First of all, you can have generalizations of the Leggett-Garg inequalities to many times. And at n times, what we do, we don't take all the correlators, we take a so-called n cycle. So 1, 2, 2, 3, and so on, up to the 1n correlator. And the Leggett-Garg inequalities at n times look something like this, plus a bunch of variants with an odd number of minus signs. And it's straightforward, but somewhat lengthy to show that the whole story around Fein's theorem generalizes to this situation. What is, of course, the question to ask, what sort of new things happen when you go to more times? Well, here's what happens when you go to 5 or more times. As I just said here, you normally fix only a subset of the correlators, that is an n cycle. But at 5 times, there are actually 10 correlators. In a Leggett-Garg test, you would only fix 5. What happens if you fix all 10? So that corresponds to going to a larger data set than you normally use in a Leggett-Garg test. What you find is that there are new conditions that are independent of the Leggett-Garg inequalities. Avis et al. In 2010 proposed these conditions, the so-called pentagon inequalities. So the sum here is over all 10 correlators. What they indicate is that there are new types of interference terms here, which can't be seen in any of the standard Leggett-Garg tests at 2, 3, 4, or 5 times. So you get this sort of new feature that arises in 5 or more times. And these generalize actually to n times, where you get similar sorts of inequalities. For those of you who are familiar with polytope constructions, there's a mathematical interpretation of these things, which is quite interesting to look into. Interestingly, these have never been tested experimentally. So with Cheyenne Majidi and Ramon Laflamme, we dreamed up some situations in a 5-level system in which we thought an experimental test might be possible in the near future. So this would be interesting because you testing some quantum effect that really just can't be reached by any of the more standard Leggett-Garg tests. The second thing we're interested in is higher order correlators. So normally you just measure the first and second order moments. Measurements have been contemplated of third-order correlators. So this is an extended data set, including a third-order correlator. And I first actually noticed such high-order conditions by one of Alok's papers in 2018. And I subsequently got interested in trying to figure out what are then the necessary and sufficient conditions for macrorealism on this extended data set. Turns out actually to be quite easy. So there are actually 8 conditions, and they all have exactly this form. It's just the sum with varying minus signs on the 3 averages, the 3 correlators, and the third order correlator. Interestingly, when you do this, you actually fix the underlying probability uniquely. So if you measure 3 times, if you measure first, second, and third order correlators, that just completely fixes the underlying probability, and then the then necessary and sufficient conditions are just quite simply the condition that this has to be positive. And then you can generalize this quite easily to n times and nth order correlators. More experimental tests could be of interest to test these sorts of conditions too. A third possibility concerns what happens when you go to higher dimensional Hilbert spaces. You don't need to concentrate on a dichotomic variable. You could have a 3-valued variable or 4-valued variable. The way to handle this is just to use more than one dichotomic variable at each time. So at a 3-level system, you need 2 dichotomic variables to say which state the system's in. And Clement Morby and I figured out how to do necessary and sufficient conditions in this situation also. What are the new possibilities here? Well, there are some very intriguing possibilities that have been investigated in a number of recent papers. So let's look at n equals 3, for instance. The dichotomic variable might be something like that. It's +1 on the 1 and 2 states and -1 on the 3 state. Now, the interesting thing that happens here is that when you measure Q and the correlators, you can do it in 2 different ways. So you can do a so-called Luders measurement in which you basically say, is Q in the 3 state or not? That's the normal sort of Leggett-Garg measurement that we would do. However, you could do something else more fine-grained. You could actually say, is it in the 1 or 2 or the 3 state? A so-called von Neumann measurement or degeneracy breaking one, because it collapses the wave function on these 1 and 2 states. And then you construct the probability from this more fine-grained probability. You get, in general, a different answer. It differs because of the interferences you get between the 1 and the 2 state, which appear differently in these 2 different measurements. Now, when you do a Luders measurement, the Leggett-Garg inequalities must obey, in quantum mechanics, the Luders bound. So classically, you get 0 on the right-hand side. But with a Luders measurement, you can go down to -1/2. And that's the parallel of the Cyrilson bound in Bell inequalities. But remarkably, with the von Neumann measurements, you can actually get lower than -1/2, which is, to some people in quantum theory, quite eyebrow-raising. But it's true. In fact, for a sufficiently large dimensional system, you can go right down to the algebraic bound of -2, in which all these correlators are -1. And I mean, that's not just a statistical paradox, it's an outright logical paradox if all of these correlators are -1, but you can get very close to that in certain models. It does seem surprising, but it's because of these interference terms in the degenerate subspace, and that it's an effect you wouldn't see in Bell inequalities. So there have been a bunch of papers exploring this. There's still some debate as to what to make of this and how to interpret it. But all these Leggett-Garg tests are about homing in on interference terms and using them to create situations which would be very striking from a classical point of view. And these Luders bounds certainly do that. So that's a very interesting topic to be looking at into the future. Now, let's talk a little bit about measurements, and just give me 30 seconds here whilst I just get something to drink. Here we go. Okay, now let's just think about methods of ensuring non-invasive measurability in the measurement process. So we do ideal negative measurements in which the detector is coupled to Q as +1. In null result implies that Q must therefore be -1. That's completely fine from a macro-realistic point of view. In quantum mechanics, it's not so fine because it still collapses the wave function. Now, what that means is that because of the wave function collapse, no signaling in time fails. Now, we're calling that no signaling in time actually measures two things. It measures interferences and it also measures disturbance of the measurement. So when we see a no signaling in time failure, it doesn't necessarily mean a non-invasive measurement. It might mean wave function collapse. Well, how do we get around this? Well, one way is to actually carefully choose the parameters of the experiment so that this is actually always satisfied, like choose the initial state. And in the recent experiment in Sinha's lab, that's actually what they did. And then the no signaling in time condition can be used as a check on non-invasiveness. I made a different suggestion, which is to note the following, that when you compute the correlator, in quantum mechanics, it looks like this. So it's actually diagonal in this Q1 hat. So you can actually do a diagonalization procedure at the first time that doesn't, in fact, affect the value of the correlator. And when you do that, no signaling in time then becomes satisfied from the quantum mechanical point of view. Now, I think some earlier experiments have actually observed this as a possibility, but in a recent paper, I sort of expanded on that and showed how you could use that as a way of improving the use of the no signaling in time condition as a check on non-invasiveness. So if you do this decoherence thing at the first time, that means that this will be satisfied in quantum mechanics, and then any violation means that it's due to non-invasiveness or clumsiness, as it's come to be called in Leggett-Garg tests. So that could be quite useful to implement in certain experiments. Now, there is still an issue here, and I had some very interesting communication with Dipankar Home and Abasi Sinha over the last few weeks about, is the no signaling in time condition really a decisive measure of invasiveness? Koffler and Bruckner, when they first proposed this, said actually it's an average measure of invasiveness, and it is. It means that you could have two lots of invasiveness down the two possible paths, which cancel each other out. It does need some degree of fine-tuning to make that happen, but it would be nice to actually have ways of eliminating this particular loophole in Leggett-Garg tests. In the Sinha experiment, they did something that went a long way towards addressing this, which is to impose this condition at more than one time, because in a Leggett-Garg test, you do measurements at times 1, 2, and 1, 3. And if this thing holds at both of those time intervals, you need even more fine-tuning to use invasiveness, cancelling invasiveness as an explanation. So that's pretty compelling, I would say. The most compelling thing you could do would be to actually require that this is satisfied for more than one choice of initial state, because there's two potential lots of invasiveness. You need two conditions to really nail it down. No signaling in time is one condition, but if you do it for two different initial states, that's two conditions, and that would really clear that one up. One of the things you could do is to have some sort of post-selection process going on, which basically collapses the ensemble of paths down onto a subset. And if you impose no signaling on time on two subsets of the paths, that would be another way of being more decisive and really just ruling out any possible fine-tuning stories that would explain this with invasiveness. Anyway, there's still some interesting possibilities to be explored here. Now, on a different topic, there's another way of actually doing non-invasive measurements of the correlator that avoid sequential measurements. And this is to notice that the correlator, you see, when you write it out, it's the probability that Q has the same sign at different times minus the probability it has different signs. So you're not actually interested in the value of Q, you're only interested if Q changes sign during the time interval from one to the other. So all you really need to measure is actually the product of these two, not these two individually. Now, this led me to suggest the following measurement protocol that exploits this and only measures the sign change. So notice that the correlator is the average of Q1, Q2. I'm just writing it macrorealistically here, which you can then, in a simpler arrangement, you can write it in terms of Q2 minus Q1. So you see, all you really need to measure here is just one thing, which is Q2 minus Q1. So can you devise a measurement that just measures this one variable? Well, you can. You make one assumption, and you assume that there's a velocity, which is v, which is q dot. Normally in Leggett-Garg tests, you don't assume very much about the dynamics, but if you will just allow me this one additional assumption, then I can then measure Q2 minus Q1. You see Q2 minus Q1 is then just the time integral of V2. And how do we measure it, a time average? Well, you just use a weak coupling to a detector continuously in time, and it's very easy then just to measure the time average of V. So you can measure this thing directly using this, this weak coupling. And then you need to make one other assumption in order to be able to interpret the results, and that's that Q changes sign only once during the time intervals. Now, this is actually true in a number of models. If you, because recall they're often sort of periodically oscillating, but if you restrict, say, less than half a cycle, to a good approximation, you do actually only get one sign change, and it includes regions in which there is some substantial violation. So you can actually make this work, and it has in fact been implemented experimentally in Ramon Laflamme's lab in 2019. Let me just show you what this looks like pictorially so you can see why it's an approximately non-invasive protocol. So let's suppose that you take Q, for simplicity, you've got a continuous variable X and you take Q to be the sign of that. Now, what you do basically is have a waiting detector that just sits at the origin and just waits for the particle to cross. And if the particle doesn't cross, the detector stays in its ground state. Most of the time, the particle will cross the origin, but because it's a very weak detector, it will still stay in its ground state. But some small fraction of the time, lambda squared, it will get excited to the one state. And those are the ones that you're interested in. So all of this looks fine. And you see it's just a one-shot measurement. There's only a single interaction with the detector here. There is one thing that can happen that messes up the results, which is that the measurement causes the back reaction, which will cause a fraction of the trajectories to go back over the detector and unclick the detector. So it goes from the one state back to the zero state. But now here's the key thing, because the detector is very weak, the number of fraction of paths that do that is only lambda to the fourth. So it's much smaller than the effect that we're trying to measure. So weak measurements are generally a little bit fraught because the effect you're measuring is the same as the invasiveness, but it's not the case here, and it's because you've just got a single interaction. So I would argue that this is in fact an approximately non-invasive measurement for reasons very different to the normal ones to do with ideal negative measurements. Okay, coming on to the last part of the talk. Interferometric experiments and simple harmonic oscillators. We are interested in approaching macroscopicity, and interferometric experiments have been carried out now for very large molecules. So it is natural in Leggett-Garg tests to see if we can modify those. It's natural to see if we can modify interferometric experiments into Leggett-Garg tests. And Alok Pan first pointed this out to me in a recent paper of his. And actually inspired by that, I got together with some students and started looking at the simple double slit experiment and turning that into a Leggett-Garg test. I'd be very surprised if this hasn't been done before, but nevertheless, there's some interesting results here. So you can very easily make this a two-time Leggett-Garg test. You define a variable Q, at the screen, which is plus or minus 1, depending on which slit you go through. At the slits. And then at the screen, you define a region, small region delta, and then say that Q is plus or minus 1, depending on whether or not you're in delta or not. And then you simply have some 2-time Leggett-Garg inequalities, which look like this. And these also are, in fact, the path probabilities. So these are quasi-probabilities for the paths. And if positive, they are actually probabilities for the paths in the double slit experiment. Now, the results of this are as follows. It's very easy to find Leggett-Garg violations for a variety of parameters. So macroscopic realism is violated. There is another measure of classicality, of course, which is destructive interference. And how does that enter in this test? Well, you find that every time there's an LG2 violation, there's always destructive interference. So these two measures of non-classicality are clearly related. Interestingly, the converse is not necessarily true. Destructive interference doesn't necessarily imply LG2 violation in this particular situation. Now, what that means actually is that even in the face of destructive interference, you can assign probabilities to the paths indirectly. So somewhat counter to the normal law that we're told about the double slit experiment. So the story about the boundary between classical and quantum is a bit more subtle than what we're told. So destructive interference is not necessarily the most decisive measure of non-classical behavior in this particular situation. Now, what Alok did was something different. He looked at the Mach-Zehnder interferometer, and there Leggett-Garg violation and destructive interference turn out, in fact, to be logically the same. So that situation doesn't have this particular feature. Now, we're just coming up to the end here. One final thing. Another very interesting area has been harmonic wells. Many macroscopic systems can be modeled by such wells, and this inspired Sugato Boza in London and collaborators to look at a Leggett-Garg approach to the harmonic oscillator using a dichotomic variable, which is simply, are you on the left or right-hand side of the origin? And then they used, sorry, this is a proposed experiment, not an actual one. And then they contemplated using ideal negative measurements to determine whether or not you're on the right or the left of the origin in order to measure the correlator. This situation actually could also be measured using the continuous in time velocity measurement that I proposed earlier. You could just have a detector very tightly localized around the origin that just sits there and waits for the particle to cross. Now, through numerical calculations, what they found is you can actually get violations of the 4-time Leggett-Garg inequalities even for a coherent state, which we often regard as a very classical sort of state. And it has positive Wigner function, which causes us to think of it as classical. Nevertheless, you can still get significant Leggett-Garg violations. This is something to do with the projection that goes on in the measurements. The chopping makes the Wigner function get negativity, but there's a story there yet to be fleshed out, which will be very interesting. Inspired by this, Clement Morby and I started looking at correlators for the simple harmonic oscillator and for bound systems more generally. What we found actually is that the correlators can be calculated analytically for all sorts of interesting experimentally accessible states, 0, first and second excited states and superpositions. Some of them actually have some rather simpler results. Calculations are a lot more complicated than the spin systems, but there are interesting approximations available. We found, for instance, in the first excited state, to a good approximation, the correlator is just a cosine, exactly like the simple spin model. So very easily, we find Leggett-Garg inequalities. So generally, there could be a whole bunch of interesting states here that are easy to implement experimentally in this potentially macroscopic system in which you can find good violations. One other thing that Clement found, instead of taking Q to just be the sine of X, you have a more interesting possibility, which is to define some region AB, which you can choose. It can be very small, very large, and then you say Q is plus or minus 1, depending on whether or not you're inside or outside. And then what we find is that even in the ground state, you can get violations of the two-time inequalities. So for the simplest possible state, you can still get violations, which sort of reiterates the story up here to do with positive eigenfunction. Okay, that is, we are just upon the hour now, and that brings me to the end. So just to summarize, the first part of the talk, I showed you how to generalize the standard Leggett-Garg approach for 2, 3, 4 times to necessary and sufficient conditions, giving more decisive tests, new experimental possibilities. This was extended to larger data sets, more times, higher order correlators, many valued variables, and these give some interesting possibilities for future experiments. I remain very interested in these two problems, alternative methods for non-invasiveness, which has become very relevant to recent experiments. And then finally, interferometric experiments, simple harmonic oscillators. These are situations in which macroscopicity could be approached and remain of theoretical and experimental interest. So that's it. Thank you very much.
Thank you very much for the beautiful and intriguing talk. And there will be questions. I mean, should I read it for you? There's one question from the student.
I see it. Yes, there's a question in the chat.
Yeah.
Right. Does the bound of the Leggett-Garg inequality depend on the inner product structure on the Hilbert space? Well, let's see. So macrorealistically, that's not the case, but in quantum theory, there are certain bounds like the Luder's bound. It doesn't, as far as I'm aware, depend on the particular inner product structure. I mean, it's just a property of quantum theory that the bounds can, the violations can get down to certain levels. Please elaborate more on non-invasive measurement. That is a very big topic, which I've tried to elaborate on during the talk. But the general story is that, as I said at the beginning, towards the beginning of the talk, that whenever you measure these correlators, you have to be certain that the value of the correlator has come from the underlying realistic properties of the system and not from the effects of the measurement. So you have to be sure that there's not some glitch in the experimental apparatus that's not actually producing it. So we need all these. The only really convincing way of doing this is to make the Q equals plus and 1 states space-like separated. That's the only convincing way of doing a non-invasive measurement. For ones that are closer, you need more checks, like ideal negative measurements, or some of the techniques that I was described and checks on them. But I think this remains one of the really outstanding problems of the field, to get a really convincing loophole-free test. The recent experiment by Sinha is getting very close to that, I would say.
Thank you. Is there any question?
Alok, I've raised a
hand,
but
okay, yeah.
I don't know whether you see the hand. Yeah. So thanks
I don't see, yes.
Jonathan, for the very kind comments on our recently concluded experiments. So I had a question regarding your more than one choice of initial state. This is something you had also discussed in our email correspondences.
Yes.
But then, when you say more than one choice of initial state, now the state, let us consider our experiment where it is a photon, right? So now the state is something which has to be, sort of has to have a role to play in the experiment thereafter, right? Like, I mean, so we are going to do an LGI violation 2 times, 3 times, whatever. But then suppose I take a photon, then it has a polarization state. Then if I change the polarization, that's the thing that naturally comes to my mind, that I can, change its polarization state and it's a different photon. How does that have any ramification on the experiment that we would do for the LGI violation? I mean, it's a different photon, it has a different state. So,
well, it's a good question. I'm not an experimentalist, as you know, so this is a theorist speculating here. In a given experiment, you may not have the freedom to make that choice of changing the initial state. Both depending on what you're measuring and depending on your experimental resources. But in my theorist's mind, I'm imagining that I get to choose an initial state at T0, and then when it arrives at T1, I'm imagining I can tune it so that the probabilities of being incurred plus minus 1 can be varied. Now, those, theoretically, in a simple spin system, I could do that depending on how I choose the initial state. Now, a very key point here is that the correlator is independent of the state at the time T1. At least in simple models, anyway. Most simple models, the correlator doesn't depend very much on the state.
Right.
But the no signaling in time condition is different for different initial states because you get different degrees of probability flowing down the 2 arms. So by checking the no signaling time condition for 2 different states, you're checking the condition for 2 different probability flows. And it seems to me if there's any invasiveness present, it shouldn't depend on how much probability is flowing through. It should be to do with something that's going on at the Q equals plus 1 point and the Q equals minus 1 point. It therefore seems natural if you can change the probability flow in the different arms of the interferometer, that can rule out the possibility that you're getting a cancellation of invasiveness. So that's the loose idea there.
Yeah. I mean, you did speak like a theorist, which is of course fine. But then, having said that, if do you think that what we have done, which of course said very well, that we have actually done it for different times. So is that going to be an equivalent to different states, which seems slightly less experimentally friendly to me than the different times, because time is something which is anyway evolving. So I can do things at different times more naturally than having this change of state occur for the different correlators. Because the problem that comes about with the change of state is that it brings its own error, right? So I mean, the whole point about these experiments is that we are trying to do non-invasive measurements, and there is invasiveness in terms of experimental errors. So so then now, if I were to say that this is that's why this question comes to my mind: does the choice of the different state actually matter? Or is it just enough for it to be some other state? Because if the choice matters, then that comes with its own attendant error. And that might actually compete with whatever I'm trying to rule out because of this averaging that, you pointed out could happen.
Yes, I can see from what you're saying about your experiment that tinkering around with the initial state might do more damage than
that's kind of what
damage than good.
So there are therefore other ways. So as you say, if you vary the time, it then renders this cancelling out process of invasiveness to be less. It's then fine tuning on top of fine tuning, basically.
Right.
So that is, I would agree, a compelling reason. There is this other proposal that I hadn't mentioned. I can't remember if I mentioned in the email, which is to do a post-selection later on.
Yes, you did.
Which just collapses. Now that doesn't. You get to keep your initial state and your times, but I'm just saying. Supposing I came in at the very end after you've finished all the run, and I just collapsed down the trajectories onto subsets, and then check no signaling in time on those.
Now that is something one can actually check with existing data.
Right. Okay.
I mean, so that I mean, we are thinking about that. I mean, that suggestion is actually very interesting. Yeah.
That would be interesting.
Sorry.
Yeah.
Yeah, please. I have one more question. I'll ask after others.
So just to tell you that is when the state change matters. I mean, what this doesn't mean by the changing the state during the experiment. For example, you did the experiment with one state, then you change the state. Maybe your notion learning condition is satisfied in somehow. But the thing is that the whole scenario is changed because when you change the state of quantum state, your lambda distribution, that the quantic distributions, I mean, what the hidden variable models, the lambda changes. So in such a case, you are actually calculating computing the Leggett-Garg inequalities for two different lambdas. So how it is related to the real experiment? I mean, how can you compare these things? This is my question to both Jonathan and to Urbusi. I didn't understand the things.
Jonathan has to go first because it's his idea.
I could just answer that briefly. I mean, as I said earlier, this is a theorist speculating on what an experimentalist might be able to do. So theoretically, but changing the state doesn't change the correlator. It does change the no signaling in time. So it would be a giveaway of any invasiveness. But I can imagine that your experiment and many others might have such dependence on the initial state that possibility isn't there.
No, my question was different. My question was not experimental. My question is a little conceptual. That if you change your psi, in such a case, you changing your distribution of lambdas. You cannot claim that for the two different psi, different initial state, you have the same lambda. Then you can do it, but you have to assume this is an assumption. Right. So if lambda changes.
What is lambda in this?
I mean, the hidden variable.
Okay, sure.
So there is some sort of assumption that everything, this entire distribution remains constant. If I actually do
entire distribution of lambdas remain same for the same two states. But this brings you to the interpretation of the whether for the two different psi you have the same lambda distributions or not. So that's psiontic, psi epistemic description that will appear here. So that's why I really didn't get this point. Maybe I can discuss later on. Okay, Urbusi, you had another question.
Yeah, I had a question regarding my favorite topic. So that was the double slit slide that Jonathan had. Yep. And of course, I have seen Alok's work on the Mach-Zehnder approach. I actually just missed the point a little bit that, a double slit is in fact, similar to a Mach-Zehnder. So you can, of course, make a double slit behave like a Mach-Zehnder. So what is the additional feature that you have, identified in the slit scenario? Which will bring about some more nuances than the Mach-Zehnder one. So I just wanted to recap that a little bit, that discussion.
Alok may be able to answer that more than I. But the thing, the Mach-Zehnder is like a more restricted version of the double slit. So if I got to, in my version of the double slit, you measure whether or not the particles arrived at a certain point on the screen or not, in some tiny region or not. But but I have in mind it could arrive at any